So we're now going to talk just a little bit about how integers are stored. Well, it depends on the computer you're using, of course, but if you're using a 64-bit computer, as most of us are, then what happens is the following. Well, okay, let me not use a 64-bit computer, but let's use an 8-bit computer. So this means the computer stores stuff in chunks of 8 bits, and a bit is either a 0 or a 1. So for a computer, you may have heard everything is just zeros and ones. But let's see here. So we have 1, 2, 3, 4, 5, 6, 7, 8. So here I have 8 bits. So this would be like the fundamental chunk inside of an 8-bit computer. And 8 bits is called a byte. And then you would have 0, 1, 1, something like this here. And each such chunk would be given a data type, or a collection of such chunks could be given a data type. But if it's the data type integer, what happens then? Well, what happens is that these guys here are interpreted as, so I'm going to lie a little bit now, and then I'm going to tell the truth at the end. So these guys here, the 7 first bits starting from the right, are just the binary representation of a number. And this guy here determines if it's plus or minus. So if it's 0, it's a plus, and if it's 1, it's a minus, okay? So this integer here is a positive integer. And then each of these guys here give me one digit of the binary number. So this binary number here would be 0, 0, 1, 1, 0, 1, 1, 0. And I can write it in parentheses with a 2, just to indicate that this is to be interpreted as a binary number. And if I write out what this means, this is 0 times 2 to the 0, plus 1 times 2 to the 1, plus 1 times 2 to the 2, plus 0 times 2 to the 3, and then it continues like this. So 1 times 2 to the 4, 1 times 2 to the 5, and then 0 times 2 to the 6, and 0 times 2 to the 7. So let's not write those up. So of course this thing here would be then 2 to the 1, so that's a 2, 1, 2 to the 4, so that's a 4, no 8s, but a 16, and a 32. So I'm getting this. So this would be 6, 22, 54. So this thing here would be how this computer stores the number 54 in its memory. And if this was a 1, it would be minus 54. Well, not really. So I'm lying a little bit, because this would be a stupid way of doing this. And to see why, let's go down to of course these don't exist, but to explain why, let's look at what happens in a 3-bit computer. So in a 3-bit computer, integers would be stored by analogy using 2 bits here. So let's say put it 0, 1, and then a bit here for the sign. Let's call it a 1 also. So this would be minus 2. So let's now see, let's make a list of all the numbers that a 3-bit computer could then represent using this logic, and see why it's stupid, and then also explain how to fix it. So we would have 0, 0, 0. That's a combination that would give 0. 0, 0, 1 would give 1. 0, 1, 0 would give 2. 0, 1, 1 would give 3. And then 1, 0, 0 would give, by what I've said, minus 0. And then 1, 0, 1 would give minus 1. 1, 1, 0 would be minus 2. And then 1, 1, 1 would be minus 3. So this is a stupid way of doing things, because I'm now representing 0 twice. So that's, I mean, it's not wasting a lot of space, which is not the only reason, but it's one reason. So what you do is you use the 2's complement, it's called. In this method, we're saying that, well, okay, this is a bad way to assign numbers to these guys. Let's keep it for the positive guys, but let's do something more smart for the negative guys. So let's just think, okay, in terms of what binary numbers these represent, so let's just continue the list. So here we had 0, 1, 2, 3, and if we just think of this as a binary number, this thing here would be a 4, this would be a 5, this would be a 6, and this would be a 7. Now, we want these guys to represent negative integers. So what negative integers are they supposed to represent? Well, if I continue this list, the next thing would be this guy, right? 8. But in a 3-bit computer, I cannot represent stuff that requires 4 bits. So in a 3-bit computer, this would overflow. You would just throw away this guy, and this thing here would be equal to 0. And then it turns out that when you're constructing the hardware, if you now think like this, so what meaning should I give to, well, let's say 7. Well, if I add 7 to 1, then I would get 1, 0, 0, 0. So if I add 7 to 1 in a 3-bit computer, I'm getting 0. So 7 should be equal to -1. Similarly, this should be equal to -2, this should be equal to -3, and this should be equal to -4. So this is what 2's complement means. You're assigning these guys the negative values corresponding to the guys up here that they kill. And of course, this guy kills himself. 4 plus 4 is 8. So this 4 guy here is then instead given the meaning -4. So then we ignore this, and now we have the list of what these integers mean. And exactly the same thing is done in an 8-bit computer or in a 64-bit computer, except there are many more bits to keep track of.